Hello, this is Alfonso Landaverde. I am here to discuss my Lab O1 report. And so yeah, let's just get into it. So for introduction, this lab was all about measuring constant motion. And in order to do that, we have to understand Newton's first law, which is that an object will continue its state of motion as long as another force is not acting upon it. And so that goes into this one with velocity, because we are assuming a ball has constant velocity, and we try to simulate that. And in order to do that, we have to know a formula like this one, which is the constant velocity formula, we'll call it, because velocity final equals velocity initial plus the net forces acting on an object times the change in time over its mass. And since it's constant velocity, we assume that the net forces is equal to 0, which cancels out the entire second term. So you're just left with the initial velocity equals the final velocity. And so that means that we are ignoring some important forces that are acting on the system, whether it be vertical forces like gravity or normal, or horizontal forces that will change the horizontal motion like friction or air resistance. And so now we will get right into it with looking at our original video. There it is. It was a little choppy, so we'll play it one more time. And then we took that video and we put it onto this tracker, and we started recording from the first instance that the full ball was on screen. Well, let me click actually to the last instance that the full ball was on screen. And from there, we tried to the best of our ability, equidistantly set all the different data points, and then run the tracker. And so that's where some human error can be involved, because we try our best, but obviously I did not equidistantly set all of these things, nor did I even perfectly set the end time to when the ball was still fully in screen, because as you can see on the last one, the ball is partially out of the screen. But that isn't too important. Now I want to open up and show you all my code. This will be our So that was our experimental model following the original video, and this will be our predicted model. And our predicted model is, simulated through this code right here. And so we plugged the numbers into the velocity formula to get that the initial velocity, we found the average velocity, which will be our constant velocity. And so we just did change in position over change in time, which got us 2.902 and the rest. We just kept it exact, but we could fix it if we really wanted. And the time we found from the last instance that the ball was fully on screen, at least from our simulated model, or I guess experimental model. And so then we use the important formulas that we know the second term will cancel out of anyway. And then we use the position update formula, which will, of course, update the position in our simulation. And now we run it. And when we run it, we see the same constant movement to the right. We see the same even slope through the positive x-axis versus time. And then we also see a constant velocity on the graph under. And so now we compare the two, the observed and predicted. And we see that the observed slightly outpaces the predicted. Its change in position rapidly grows throughout the length of the recording. And that could be as a result of us ignoring forces like momentum or like the ball's acceleration and things of that nature. The forces that we assumed to be 0 were not 0. And because of that, it does not completely match the predicted data. And we can also take note that the predicted data is 100% constant. Every single point is equidistant, and it's just nicer because it truly does run as if the net forces were 0. And so that comparison shows us that we could not ignore all the forces, or there was not no net force acting on the system. And so those differences, as mentioned, could be due to human error, or they could be to forces that we had ignored during our experiment. And so now we have two questions, which are, if we were to flip the x-axis and change the position from the ball from going through the positive x-axis to the negative x-axis, what would that do? And that would simply make the slope point in the negative direction, so it'd have a negative slope. And since the slope is now in a different direction, the velocity is also pointing in that same direction, or it is going to be also in the negative direction as a result. And then the pushes and pulls, are we able to measure them, and are we able to know just how many there are in the system? No. We are only able to measure the effects of those pushes and pulls, but it is difficult to quantify how many there are, or to quantify their effects on the system, because I'd need a more advanced simulator, or I'd need to become a better physicist, which both aren't the case at the moment. Okay, that's it. The end.